Hello, Mr. Wakefield here. We're looking at section 7.1 now. Remember, we skipped chapter 6, so that's why we're going straight to chapter 7 here. And in the first couple sections here, first three sections actually, of chapter 7, we'll be looking at this thing called sequences. All right, I'm sure you've heard that word before, but what does it officially mean, mathematically speaking? Basically, for the most part, it's similar to a function, all right? And I kind of have a comparison here that I wrote down up here on the top. I gave you a basic-looking function that we've seen this type of thing many times in this class. All right, f of x equal to 6x minus 3. Usually sequences are done in the same way, where the difference is that instead of f, they use the letter a usually. Not always, but usually. And then instead of x being the thing that you plug into, okay, you can see I just plugged in the number 1 here just as an example, into x. Instead of plugging into x, we plug into n, okay, the letter n. And so you can see 6n minus 3 is very similar to 6x minus 3. And it creates these things called sequences, all right? And so just like doing f of 1, all right, a sub 1, and I say sub because the 1 is written underneath, so sub. Okay, so the sub usually is referring to something underneath, right? Like a submarine. So a sub 1, all right, and we've seen that kind of notation before with certain things, but that's how you write it with sequences. The name of the function, which is usually a instead of f, all right, is here, and then underneath that is the thing that gets plugged in, which it comes from usually the variable n. So just like f of 1, we got a sub 1, and it gives you the same answer since it's basically the same function. It's just that you use the letter n instead of the letter x. And so the big difference, though, between a normal f of x function and a sequence formula is that the domain, and remember, domain is the set of all numbers, at least when you have a function formula. It's a set of all numbers that you could plug into the formula and actually get an answer out. Okay, actually get an answer. And so with sequences, though, and this is without exception, with the sequences, you can only plug in 1, 2, 3, 4, 5, 6, 7, those types of numbers, positive whole numbers, in other words. And this list of things you can plug in goes all the way up to infinity, but it's just the positive whole numbers. It's not decimals or fractions that aren't whole numbers, that don't simplify to whole numbers when you put them in lowest terms. All right, like 5/3, for example, or 1.5. Those kinds of things you're not going to plug into a sequence when you have the sequence formula, okay? You just numbers like this, all right? So just wanted to give you a heads up on that. And what do you think of, by the way, when you think of the word sequence? I know that when I hear about sequences anywhere, you typically think of a pattern. And so that, as you're going to notice here today when we get into the sequence problems, you're going to see that they typically follow a pattern, all right? In a sense, they always follow a pattern. It's just that sometimes the pattern's a little bit more obvious than it is in other problems. But it will always follow a pattern in one way or another when you have a sequence formula, okay? So I just wanted to fill you in on that as well. But let's go and get started here with the first set of problems. It gives us, in the first two problems anyway, it gives us one of these sequence formulas. In fact, the first one is the one I already mentioned at the top of the sheet. So what it says is it just says write the first 5 terms of the sequence. What they mean by that is, and remember, the domain is what again? The domain is 1, 2, 3, 4, 5, 6, and then it goes on and on and on. But if they say the first 5 terms, you guys, what they mean is they mean to plug in 1, 2, 3, 4, 5. Okay, if they said, oh, just give me the first 3 terms of the sequence, for example, then you would just plug in 1, 2, 3. Okay, so let's do that right now. Let's plug in 1, 2, 3, 4, 5. If I do that, I get a sub 1, a sub 2, a sub 3, and then a sub 4 and a sub 5, right? Let's see what those 5 things are equal to. All right, so it's just like plugging a number. It's just like plugging 5 numbers into f of x, okay, and getting 5 answers, okay, because again, this is very similar to f of x, like we did many times this semester. So what do we get if we plug in 1? We get 6 times 1 minus 3. Just like f of x, you guys, whatever number replaces the n right here, replaces the n here. Okay, just like whatever replaces the x on the left-hand side, replaces the x on the other side, okay? If the x gets replaced by 1 right here, the x gets replaced by 1 on the other side of the equal sign. Okay, if n gets replaced by 1, then n gets replaced by 1 here. Very, very similar thing, thankfully, to what we have with functions. And so doing order of operations like we always do after we plug the number into a function, we get 6 minus 3, which is 3. And let's just do that with all the rest of these, okay? In fact, I'll go ahead and just plug it in here first. Okay. And then we'll figure them all out one at a time here. All right. Again, order of operations says to do multiplication before subtraction. So we get 9. This one would be 18 minus 3 equal to 15. 24 minus 3 equal to 21. And finally, 30 minus 3 equal to 27. And that's all they wanted you to do, okay? So they just wanted you to figure out the first 5 terms of the sequence. You don't have to write down what I'm about to write down right now to finish off this problem, but sequences usually are written with commas, and you'll see that in these 2 examples down here, okay? So, again, completely optional. Unless they tell you to write it like this, you don't have to. They just wanted to know what the first 5 terms were. We figured that out. I circled them. All right, but just to let you know, this is usually how it's written, and then after the last term, you go dot, dot, dot. And that indicates that the sequence goes on forever, because we could plug in 6, we could plug in 7, we could plug in 8, and so on all the way up to infinity. We don't have to stop at 5. We stopped at 5 here because that's all that they asked for in the directions, but theoretically, to figure out what a sequence is, you could just keep on going and going and going. And now remember, again, another thing that's not asked for in this problem, so this is optional, but just to talk to you about it, can you see the pattern here? Just don't look up here at the formula. Just look at the sequence right here written down at the bottom. Can you see the pattern here? Can you see that each number is 6 more than the previous one? And since that is true, since it's obvious that that's the pattern, okay, 3 plus 6 is 9, 9 plus 6 is 15, 15 plus 6 is 21, and so on. Can you see that the next term would be 33? Because 27 plus 6 is 33. And then the next term after that would be 39, because you add 6 again. All right, so a lot of times when you get a sequence, not necessarily all the time, but a lot of times, okay, the pattern is going to be obvious, and you're going to be able to figure out the next term. Okay, and always double check. If they give you a formula, always double check to make sure that that really is the next term, because sometimes looks can be deceiving in math. Okay, we got to be certain about it, but it appears obvious, all right, that the next term is 33 and the next term is 39. We could plug it in to make sure, and if you do, I promise you those will really be the answers. But there is a pattern normally that's obvious when you do sequences. All right, let's do the next one. So again, first 5 terms. A sub 1, A sub 2, A sub 3, all the way down to A sub 5. Okay? And so what are these things? Negative 1 to the 1 minus 1 power, bracket 1 plus 1. Okay, now, as we learned back in the chapter 4 in particular, when you have an operation inside of your exponent, it's as if there's an invisible parenthesis around the exponent 1 minus 1 right there. And you don't have to write that down the parentheses. It can be invisible. But it's a reminder that you have to, since parentheses come before exponents, you have to calculate what the exponent's equal to before you can take negative 1 to that power. Okay, we did that back at the end of chapter 4 when we saw, for example, you had like the k number being multiplied by the t number that you plugged in, and you had to multiply it before you took e to that power. All right, there was a lot of problems like that. Anyway, the point is that the exponent has to be calculated before you can actually use it by taking negative 1 to that power. So since that is like an invisible parenthesis around 1 minus 1, and since this is also a parenthesis that's separate from the 1 minus 1, you can always do two different parentheses at the same time as long as they're separate from each other. And 1 minus 1 is separate from 1 plus 1, so I can do both of those at the same time. The 0 and the 2 can be calculated simultaneously. And now that I have done all the parentheses, in other words, the only parentheses I have left here are just single numbers on the inside. So we're done with parentheses when the parentheses just have single numbers on the inside. We then move to the exponent step in order of operations. Again, PEMDAS, right? That's order of operations. Parentheses come before exponents. Exponents come before multiplication. Okay, so we need to do the exponent. -1 to the 0 power is equal to 1, because anything to the 0 power is equal to 1. And then finally, multiplication, our final answer is 2. Let's do that again. Same exact process, we're just plugging in a different number. So you figure out the two parentheses first, all right? I don't figure out this parenthesis here, -1, because it's already a single number on the inside. So that parenthesis is basically done, okay? 2 minus 1 and 2 plus 1, what are those things equal to? Let's write those down. We get 1 for the exponent and then 3 inside of that last bracket right there. And then we do exponents before multiplication. So that gives me -3, doesn't it? Let's keep going. And you'll start to see a pattern developing as I do more of these, going down towards AA5 at the bottom here. So we do what? We do the exponent, and meaning the figure out what the exponent's equal to. And we do the 3 plus 1 at the same time for the same reasons as we did in the previous couple of terms up here at the top. So we get -1 squared times 4. That is 1 times 4 equal to 4. Can you start to see a pattern developing here? And double check to make sure, but doesn't it appear, let's follow it here. We got +2, -3, +4. Doesn't it seem like the next one should be -5 and then +6? Okay, because it appears that the signs are alternating. Maybe it's a little bit early for me to be saying that after only 3 terms, but again, this is part of the kinds of things that that are good to think about, though. All right, but again, we're going to double check anyway. So even if it is too early for me to think about that, maybe it's too early to assume. In other words, and we should never assume completely in math. Okay, we should always again double check to make sure. But it appears that the next one's going to be -5. But yeah, it appears definitely the next number is going to have 5 in it because it's 2, 3, 4. But because of the alternating signs, I forgot the exponent there. But because of the alternating signs, it appears that the next one's going to be negative. Let's see. Yeah, again, the exponent is going to be -1 to the third is -1 times 5 is going to be. Should put brackets there, even though it's not completely necessary. But so we get -5 right there. Okay. And so, as I thought, and so now it's becoming even more obvious that the next one's going to be +6, isn't it? But again, let's just double check to make sure. All right, let's not ever assume stuff in math without being sure. So we get, again, the exponent is equal to what? We're not taking it to the power yet. We're just figuring out what the exponent's equal to first, excuse me. And so that's going to be 4 for the exponent. And then the second bracket is 6. And so -1 to the 4th power, if you multiply -1 4 times, all right, that is going to be equal to +1. +1 times 6, as we suspected, is equal to 6. So 2. -3, 4, -5, 6. What do you think the next term could be? Okay, it appears like it's going to just keep on alternating, right? So it's going to be -7, +8, -9, +10. Okay, and that's what it appears it's going to be. All right. So again, sequences typically follow patterns, right? And let me go ahead and write that down. Again, it's optional to write it down like this at the bottom with the commas and the ... at the end. But since a lot of sequences are written that way. I might as well get you guys used to that, okay? So there's how it's normally written in sequence form. Okay. Next one. This one is a special kind of sequence. This type of sequence is called a recursive sequence. It's different from the first two sequences in that you could figure out any term of the sequence, whether it's the first term or the second term, or even if it was the 29th term, okay? You can figure out the 29th term right away by just simply plugging in 29. Okay, this one's different in that you can't figure out, say, the 29th term unless you know the terms right before it, okay? And I'll show you what I mean by that here as we go through. You'll understand that. So there isn't like a formula like there was in the first two problems where you can figure out any term in the sequence anytime you want. All right, figuring out any term is dependent upon the terms right before it. So that's why it tells you right away, it gives it to you. It tells you what the first two terms are. And so since it tells us the first two terms, we just have to figure out what? We just have to figure out 3, 4, and 5, don't we? Okay, because the directions again just say to find the first 5 terms. Well, they told us what the first two were, so we're almost halfway there already. Okay, let's talk about what this last part means right here. What does this mean? It says that A3, if the n is 3 right here, and you can see that it is, n is 3, okay, then that means that A3, follow it closely here, is equal to A sub 3 minus 1. What is 3 minus 1? 3 minus 1, of course, is 2. And so the little number that's underneath the A then would be 2 right there. And then you bring down the plus right here. And then what is n minus 2 right here? Well, in this case, since A is 3, since we're trying to figure out 3 right now, okay, that would be A2, which we already determined. I brought that down. Plus, and then what is n minus 2 right here? It's 3 minus 2 in this particular case, and so that would be A1. Okay, let's do that for the other two just to get practice here. So for A4, what is this saying? 4 would be A4, A3, A2. So A4 is equal to A3 plus A2. See, the minus 1 and the minus 2 is telling you to take the original number that you normally would plug in, and there's nothing to plug into here because we don't know what these things are, but like there was in the first two problems. But the point is that that's the n number. The n number in this case is 4, and so if the n number is 4, then this must be 4 minus 1 equal to 3. And this must be 4 minus 2, so that would be A2 with the plus in between it again. Okay, so how about A5? Okay, again, can you see now that the n minus 1 and n minus 2 is just telling you to take whatever number this is right here, whatever the n number is, and just make it 1 less and 2 less? Okay, 3, 1 less would be 2, and 2 less would be 1, okay? 4, you get 3 and 2, and so for 5, you're going to get 4 and 3, aren't you? Okay? And so they're just simply telling you, because of the n minus 1 and the n minus 2, they're just telling you to plug in, or not plug in, I'm sorry, I keep on saying that. There's no plugging in here. But to take the A sub 2 term and the A sub 1 term, they're telling you to take the two previous terms in the sequence and add them together to get it equal to whatever term you're looking for. So you add the first and the second to get the third. You add the second and the third to get the fourth. You add the third and the fourth to get the fifth. All right? And it's all because n minus 1 and n minus 2 means the two previous terms, or the two previous n numbers that you would normally plug in. Okay, there's no plugging in here, but that you would normally plug in, those two previous numbers. All right, you plug them in, or in this case, they just tell you what term you are in the sequence. In this case, the second and the third, or the third and the fourth. It's those two previous things that have to get added together in order to get the current term. Okay. So just want to make sure you understand what n minus 1 and n minus 2 mean. All right. It all follows whatever the n is. Okay. n minus 1 is always 1 less than n. and minus 2 is always 2 less than n, as it appears to be when you look at it, because we know that subtraction means less. Okay, so anyway, we already know that A2 and A1 are equal to 3 and 1, so that's all you got to do is just add those together, and there's your third term. Okay, we know that the second and third term are what now? Well, I didn't know. Here's the thing. I couldn't have figured out A4 to you guys right at the beginning of the problem, because A4 was dependent upon our knowledge of the third and second term. I knew what the second term was right at the beginning of the problem. Yes, I knew that, but I didn't know what the third term was until I did this step here. That's why you got to do these problems in order here, okay? Now that I know what the third term is, I just found that out right here. It's 4. I bring that down, okay? And it will then allow me to figure out what the third and second term add up to. 7. And now that I know what the fourth term is, I then can what? I can then add the third and the fourth term together to get the fifth one. So it's kind of like a domino effect if you've ever seen dominoes knocked down before, all right? You can't knock down the fourth domino until you've knocked down the third domino. It's the same thing here. You can't figure out the fourth term until you have figured out the third term so that you can then bring it down here to add these together, and then that will tell you what the fourth term is equal to. Okay. So the fourth and the third term are what? They are, we found them out right here. The third term is 4 and the fourth term is 7. And so 7 plus 4 is 11. So the final answer here, if you put all 5 terms together, it is the 1 and the 3, and then the 4, 7, 11. Okay. Do you see a pattern there? Okay. Again, they don't ask for this, but it's just good to know. It's just good to be able to have the ability to do this for later on. Okay, can you see what the next term in the sequence appears to be? Okay, well, look at the pattern here, and the formula kind of confirms this. In fact, it does confirm this. Isn't it true that each number, as the formula confirms, isn't it true that each number, starting out with the third one, is equal to the sum of the previous 2 terms? Okay, 4 is equal to 1 plus 3. 7 is equal to 3 plus 4. 11 is equal to 4 plus 7. Okay, each number is always equal to the 2 previous numbers added together. That's why you got to know the 2 previous numbers first before you can figure out that current number. So with that in mind, what does it appear that the next number is going to be? Wouldn't it be 18? Because the 2 previous numbers add up to 18? Okay, and so that's, again, why we say that sequences are like patterns. So they have a pattern attached to them. Okay. All right. So that is finding the first 5 terms of a sequence. Now, what if I give you the sequence now, not with a formula like we did up here, but with the commas and the dot, dot, dot at the end? What if I gave you that and I said, hey, what's the next term? Well, similar to what we did here when we did the commas and the dot, 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 just for practice, let's do that similar thing here. Let's look for a pattern here. All right, there's not a set way to do this. Each problem is different, so you just got to keep on thinking about it until you figure it out. And do you see a pattern here? Well, one of the things that we learn when we look for patterns in the previous 3 problems is try to see if each number is dependent upon the previous numbers, like it was here. Do you see that this is very similar to this one here? Isn't it true that the third number is equal to the first 2 numbers added together? Isn't it true that the fourth number is equal to the previous 2 numbers added together? And so on. 3 is equal to 1 plus 2. 5 is equal to 2 plus 3. 8 is equal to 3 plus 5, and so on. 13 is equal to 5 plus 8, and it just keeps on going, right? So wouldn't it make sense then that, in fact, I'll write this down, each number, each term specifically, it equals what? The sum, in other words, remember sum means addition, equals the sum of the what? The 2 previous terms, right? Okay. And so therefore, the next term should be what? should be 34. Now, we don't have a formula to plug into to make to confirm that, but I'm not trying to trick you here, you guys, all right? If the pattern holds, if that idea that each term adds up to the sum of the two previous terms, if that holds for every single one of these numbers right here, okay, then, again, I'm not trying to trick you. That's going to end up being the answer. That's going to be the way that you figure out the next term, all right? So normally, if you had a formula, you would confirm that just to make sure that the pattern didn't suddenly change somehow. But if there's not a formula, then if it occurs with all of the terms that you see here so far, then, again, not trying to trick you, that's going to be what it is. Let's look at the next one now. Usually, it's not dependent on the previous numbers. It was on this problem here, but a lot of times it's dependent upon just a normal pattern from one number to the next. Okay, that just keeps on going all the way through. Just like right here, where it was you keep on adding 6 to each number. This one, you keep on bumping the number up by 1, but you alternate the signs. All right, the same pattern from one number to the next. Okay. What's the pattern here? Okay. Notice here that 0 plus 3 is what? 0 plus 3 is 3, but 3 plus 5 is 8. 8 plus 7 is 15. You see the pattern there? Okay. You add 3 to get to the next one. You add 5 to get to the next one. 3 plus 5 is 8. 8 plus 7 is 15. So you would think that the next one here would be plus 9, wouldn't it? Let's confirm that. 15 plus 9, is that equal to the next number? Yes, it is. Okay, so you can see a pattern is developing here. Okay, so you would expect the next one here to be plus 11, wouldn't you? Okay, and then plus 13. And that's exactly what it is. Let's just confirm that. 24 plus 11 is 35. 35 plus 13 is 48. So then what would have to be 48 then? 48 would be, and look at the pattern here. Plus 3, plus 5, plus 7, plus 9, plus 11, plus 13. The next one must be plus 15, huh? Because we keep on adding 2 more than we added before. Okay? And so what is 48 plus 15? 63. Okay? And so that's why 63 is the next term in the sequence. Okay. Now, so that's what sequences are all about. Now, we use sequences as part of a bigger thing also that we're going to introduce right now, and that is called series. Okay? You see right here it says evaluate each series. What is a series? A series uses the, let me just look at this real quick here. In fact, I'll look at them both at the same time, side by side. Why don't we do that? There we go. So this is at the top of your page right here. I'm just putting it side by side like I oftentimes do. And the sigma letter right here, it's a Greek letter, this big thing here that looks almost like a capital E. Okay, that's called the sigma letter in the Greek language. And we use a lot of Greek letters in math. You may have noticed that already in previous math classes, including this one as well. But anyway, what does sigma mean? It means to add. Add what, though? Okay, well, let me zoom in here a little bit closer so you can see it. You'll see down here at the bottom there's the number 1, and then at the top there's the number n. Now, it's not always going to say n right there. It'll usually have a number there. Okay, but whatever that number is, okay, that's where the adding stops. So it always starts here and it always ends there. What do we mean by that? Okay, what we mean is that this right here is going to be like the function formula again. Remember we did the function formulas a few minutes ago, like 6n minus 3 or like this one, for example. Okay, that's the thing that goes right here. It'll always go just to the right of the sigma letter. Okay, and we're going to plug in numbers into that function just like we did in problems 1 and 2. It's exactly the same thing, okay? But the question is what numbers do you plug in? Do we plug in the first 5 numbers again? Not necessarily. It depends on what they give you, okay? Here's how you know what to plug in. the number down here at the bottom is the first number you plug in, and the number at the top, again, it won't normally say n there, okay? It'll say whatever number that you're going to end with. So let's say, for example, that this had said 4 at the top. So you've got a 1 on the bottom and a 4 at the top. Let me just make it clear, you guys, this is not always going to be a 1 on the bottom. Now, I'll get into that in a minute. Don't worry. We'll clear that up. But let's just pretend for now that this is a 1 and this is a 4. That means that you would then plug in 1, 2, 3, 4. Okay? Just like on these problems, you plugged in 1, 2, 3, 4, 5. You would plug in 1, 2, 3, 4. Okay? What if this had said, for example, a 2 on the bottom, but then a 6 on the top? Then you would plug in 2, 3, 4, 5, 6. You'd plug in all of those numbers one at a time. You would get all of those answers. You get the A2, the A3, the A4, all the way up to A6. Because if the 6 is on top, then A6 is going to be the last one. Okay? And that's what you would do. And then what happens is that because of the sigma letter, it's telling you to add all those answers together. So that's the difference between the problems 1 and 2 up here. Is after you plug in all of those numbers, you guys, what you're going to do is you're going to add all those answers together. So, for example, if problem number 1 was one of those sigma problems, you would add all of these numbers together to get one single answer instead of having these 5 numbers be separate as 5 different answers here. Okay, but there's no sigma letter here telling you to add them together, so that's why I didn't do that. Okay, so let's look at this first problem right here. It says 1 on the bottom and it says 5 on the top. That means that I'm going to do what? I'm going to plug in, I'm going to figure out what A1 is, what A2 is, what A3 is, what A4 is, and what A5 is. I'm going to figure out all of those things, and then I'm going to add them together because the sigma letter tells me to do that. What do I plug? What is the A that I'm plugging these numbers into? It's the thing that is to the right of the sigma letter. It's that thing right there. Okay. Now remember, this thing right here, you guys, let me pull it off to the side. Okay, that is 1 over I plus 1 to the first power. Okay, when you have anything to a negative power, okay, and that's all you have is just the base, the thing that's taken to that power along with the negative power. If that's all you have, then you just simply take the base, you drop it down into the bottom, and you put a 1 on the top. We've done that a number of times this semester, especially in Chapter 4. Okay, but we also reviewed it in your prerequisite review packet that we looked at the beginning. And so it's the same thing as that, isn't it? You don't need the bracket. When the bracket's taken to the first power and there's nothing else in that denominator, you don't need the bracket if you don't want. You could keep it if you wanted to. You don't have to. And so with that in mind, you guys, that's what we're going to plug into then. And so what would this become? If I plug in 1, that would be 1 over 1 plus 1, wouldn't it? Okay. And so, of course, that's 1/2, isn't it? Remember, when you're figuring out what a fraction is equal to, remember, you figure out what the top and bottom are equal to. If there's no variables there, okay, and there isn't, you figure out what the top and bottom are equal to, and then you put it in lowest terms if you can. This is already in lowest terms, so I'll leave the 1/2 as it is. Okay. Next one here. Plug that in. You get 1/3. And please, you guys, leave these in fraction form. Don't make these into decimals. The reason why is because if you did 1/3 as a decimal, unfortunately, it's going to give you one of those decimals that covers your entire calculator screen, which means that the answer the calculator is giving you is rounded off, okay? And we don't ever want to round up before the final answer. And we're nowhere near the final answer yet. We still got to add all these things together. Okay, and plus the problem did not say to do any rounding off anyway, so you shouldn't even be rounding off the final answer. Okay, so if you're not supposed to be doing any rounding off and you have a fraction that converts to a decimal that covers your entire calculator screen, remember, in that case when it covers the whole screen, keep it in fraction form. Okay, don't try to make it into a decimal in that case, because then it's going to be a rounded off answer, which means it's not exact. And we normally need an exact answer unless the directions say that it's okay to round off. Normally. Okay, we've seen exceptions to that, but this is not one of those times. Okay. This would be 1/4, wouldn't it? This would be 1/5. Again, I'm just plugging in the rest of the numbers here. And then this one will be 1/6. 1/5 and 1/6. So, I know it'd be a lot easier to use decimals right here because we got to add fractions together, and that means you need a common denominator and all that kind of stuff. Okay. But unfortunately, we have to avoid the decimals because we need the answer to be exact. I'm going to move this over slightly to give myself some room. I'm not changing anything. I'm just moving it. Okay. A4 and A5. So, what do they want us to do here? Since the sigma letter is there, it's telling us to add the 5 answers together. Okay. How do you add a bunch of fractions together? You need a common denominator anytime you add or subtract fractions. All right. What is the least common denominator for 2, 3, 4, 5, and 6? Okay. It is actually going to be 60. All right. And the way to figure that out is, again, when you're figuring out the LCD of something, assuming that it's just constant numbers. I'm not talking about those bigger denominators with multiple terms and variables and stuff. I'm just talking about single constant numbers as your denominators. Okay, LCD, the way to figure that out is just take the biggest number, the biggest denominator, which is 6, and you keep on listing out the multiples of 6 until you find one that works for all the other denominators too. If you keep on going, it's not too long, but it is kind of long here. Eventually, you're going to find one that works for all the other denominators, and that number is 60. 60 is a multiple. In other words, it's a multiple of all the other denominators as well. In other words, 60, sorry, I apologize, that fell off the screen there, excuse me. If you list out all the multiples, eventually you get to a number, in this case 60, that is a multiple of all the other denominators too. That means that what? That means that all these other numbers divide into 60 evenly. Okay. 2 times 30 is 60, isn't it? Okay. 3 times 20 is 60. Since I can multiply 3 and 2 times something to get 60, that means that 60 is a multiple of 2 and 3. As long as you're multiplying by a normal whole number, not a fraction or a decimal. Okay. You multiply that one by 15, it'll give you 6. You multiply this one by 12, and you multiply this one by 10. What are these 5 answers going to be? Okay. This one right here is going to be 30 60ths. So I just convert it to that. Okay. This one's going to be 20 60ths. All right, so we got a little bit of arithmetic to do here. Okay. 20 60ths for that one. And so on. So this one is going to be 15 60ths. 1/5 is going to be 12 60ths. And then finally, the last one is going to be 10 60ths. All right, now that all the denominators are the same, and since we're just adding a bunch of fractions together, we can now what? We can now add the numerators together. Okay. And the denominator stays the same when you add fractions, right? So we get 30 plus 20 is 50, and then 65, 77, 87. When you get a fraction answer, we typically put it in lowest terms. All right, if I do that here, if I divide both of these by 3, I get 29 and 20. So 29 20ths is going to be your final answer right there. And yes, you could actually put that in decimal form. And the reason why I'm saying that, I know I said that earlier you shouldn't do that. The reason why I can do it this time, what makes this different is that if I do put this into my calculator, it will be a decimal that does not cover your entire screen, and therefore the calculator is then declaring that it's an exact answer. If you put that in your calculator right now, it will say 1.45, which does not cover your entire screen. That's a pretty small decimal. And so that would be okay as well. But you can leave it like this. Just put it in lowest terms. All right. If it's not already in lowest terms. Okay, so we're going to go ahead and stop the video right here. We'll come back with part 2 of section 7.1 in the next video, and we'll talk more about the sigma notation and the series when we do that, and we'll be doing that by looking at some problems on the back side of this worksheet. And so in the meantime, let me know if you have any questions. Have a good day, and again, we'll see you back for part 2.